Hello, and a warm welcome to MDPI BIPV Innovative Solutions and Energy Simulation. My name is Laura, and I will be your host. Thank you for taking the time to join us online today. We'll be starting shortly, so if anyone joins a little late, they can easily catch up. This session is being recorded, and the recording will be available on the webinar page afterwards. You will be able to find details about certificates and other information in the chat. I hope you enjoy the presentations and find the discussions insightful and inspiring. Without further ado, let's get started. So this webinar is organized by MDPI, a pioneer in open access scholarly publishing established in 1996 and headquartered in Basel, Switzerland, with the first journal Molecules. Our mission is to promote open scientific exchange across all disciplines. We publish 486 diverse journals, including 477 peer-reviewed and 9 conference journals, supported by thousands of academic experts committed to high-quality service for authors worldwide. Today's webinar is hosted by the journal Buildings. Buildings is an international peer-reviewed open access journal on building science, building engineering, and architecture, published semi-monthly online by MDPI. Today's program will begin with opening remarks from our chair, Dr. Nuria Martin Civele. This will be followed by a presentation from Professor Lorenzo Olivieri on BIPV solutions and potential in building retrofit. After that, Dr. Jesus Polo will present us modeling and simulation of BIPV systems. Each presentation will be followed by a Q&A session, and once all sessions are complete, our chair, Dr. Civele, will close the webinar. We've also selected a special issue that complements today's topic, and we'll be sharing the link in the chat box shortly if you wish to take a closer look. If you have questions, feel free to drop them in the Q&A box. We'll be sure to answer them during the Q&A sessions. And moving further, I would like to introduce the speakers we have with us today. Our webinar's chair, Dr. Nuria Martin Civele, holds a PhD in physics and serves as a senior researcher at the photovoltaic unit of CMAT. Her work has focused on research, development, and innovation in photovoltaics and building integrated photovoltaics. Professor Lorenzo Olivieri from Polytechnic University of Madrid is an experienced researcher and educator in renewable energy and energy efficiency, specializing in building integrated photovoltaics. Professor Olivieri holds degrees in mechanical engineering, renewable energy and photovoltaics, and a PhD focused on BIPV. Dr. Jesus Polo joined the Renewable Energy Division CMAT in 2003, working on developing and modeling solar radiation for solar power plants. He works on several research and development projects and collaborates with several companies in providing solar data and consultancy. And now I am pleased to invite Dr. Nuria Martin Civele to give her opening remarks and officially start this session.
So it's my pleasure to welcome you to this event entitled BIPV Innovative Solutions and Energy Simulation. As Laura said, this webinar accompanies the special issue Advances in Building Integrated Photovoltaics for Sustainable Buildings. The BIPV technology, well, this is the announcement of the special issue. The BIPV technology represents the optimal approach to combine architecture design with on-site renewable electricity production. BIPV modules integrate into the building envelope as construction products and generate photovoltaic electricity. They have demonstrated their ability to replace conventional building materials and leading to functional, visually appealing, and efficient solutions. As the demand of sustainable and energy positive buildings increases, the role of BIPV in the built environment becomes ever more significant. And this is why this special issue and this webinar is talking about this innovative technology. What I encourage you to submit contributions to this special issue. And when today we have 2 relevant experts in the field that will present different key aspects of BIPV and participate in the Q&A sessions with aim to bring together researchers and professionals to share insights and discuss implementation strategies for new and retrofit projects. So we have already seen the program. So just to remind you that we will have 2 Q&A sessions after each presentation. And now is the turn of Professor Lorenzo Olivieri. So Lorenzo, whenever you want, please.
Good morning. Welcome, everyone. So thank you very much, Nuria, Laura, all the staff for inviting me to join this very interesting webinar about the topic I am very passionate about. It's one of the most important research lines I'm working on for some years right now. So today I will share with you my point of view about BIPV solutions and potential in building retrofit. When we speak about BIPV, we speak about really energy, and we always have the same problem when we speak about energy. Energy is a very abstract concept, is a very abstract idea, really. We cannot touch energy, we cannot see energy, we can only see and touch the effects of using energy. So I would like to share with you some effects of using energy in order to train our sensibility, our intuition about the energy-related issues. So what can we do with 1 kilowatt hour? We use a lot this unit in our lives. Probably we are not able to visualize what a kilowatt hour is. So probably it can be useful to know that with 1 kilowatt hour, we can charge a smartphone about 70 times. According to the typical capacity of batteries in our smartphone today. We go for a trip by car, for instance, we can cover about 2 kilometers with this amount of energy using this fantastic car, very old car, Fiat 126, but also using much more modern cars and vehicles. We have improved a lot the safety, we have improved a lot comfort, but the energy consumption of cars and vehicles in general haven't changed a lot in the last 50 years. If we go for a run, we can cover about 10 kilometers with 1 kilowatt hour. Obviously, it depends on the weight of the runner. On average, 1 kilowatt hour is the energy required to cover 10 kilometers. We are much more efficient than cars to cover distances thanks to evolution. So why I'm speaking about these topics that they can appear a little bit far from the main topic of this session today? Well, because on average, each household in Europe consumes about 50,000 kilowatt hours each year. These data are from for the year 2023 from the Eurostat, but normally energy issues are very slow to change. So we can assume that they are similar to the consumption in this year, for instance, or in the next year also. So each household consumes the same amount of energy that is enough to charge a smartphone about 2,200 years, or to have a round trip from Madrid to Vladivostok to cover 2.5 world tours. So you can see that now we have transformed a very abstract number, a very poor number, 30,000 kilowatt hours in energy usage. So we can visualize that really it's a very big amount of energy what we need in our building on average. So you probably know that European Union has established a long-term objective to be the first climate neutral continent by the year 2050. In order to reach this goal, an intermediate goal has been established for the year 2030. According to this intermediate goal, emissions should be reduced by 55% compared to 1990. So the big question here is how can we reach these very ambitious goals? Europe is working about a lot of measures in order to improve the efficiency and reduce the energy used in several sectors of our economy. There are a lot of sectors that are not close related with buildings, but there are two of them that are very close with buildings. These measures are called Fit for 55 package. If we have a look at the Renewable Energy Directive, it has been reviewed in order to increase the share of electricity coming from renewable energy technologies. So the previous target was 52%. The new target is 42%. If we speak about buildings only, 49% of the energy used in buildings have to be produced with renewable energy technologies. Sorry. The other very relevant directive we have to consider is the Energy Performance of Building Directive. So the review of this directive establishes for the first time in a very clear way the role of solar energy in the built environment. So we have a long-term objective to have all the buildings zero emissions by the year 2050. Several intermediate steps have been established. For instance, for the year 2027, public and non-residential buildings bigger than 250 square meters should include solar technologies. Can be solar thermal, they can be solar photovoltaics. It's not defined in the directive, but we know that a solar photovoltaics use of solar energy is much more interesting and much more with a bigger potential than a solar thermal use of solar energy, the thermal use of solar energy. So in the next few years, existing building and non-residential buildings also bigger than 2,000 square meters and bigger than 750 square meters, etc., will include solar energy. So in short, we can say that there will be no buildings without solar systems in the next few years, obviously, if it's technically feasible. So we all know that rooftop PV system or distributed PV systems are already a reality. You can see here in this graph the evolution of the capacity, the PV capacity in the last years. About 1/3 of the PV capacity installed is distributed PV capacity, normally on rooftop systems. So they already are a reality. In Spain, the situation is very similar with a lot of self-consumption PV systems installed, about 500,000 PV systems already installed, with a lot of them installed in the last 3 years. But if you have a walk in the city, and these photos are from Madrid, but I think they can be similar in other cities. The typical PV system we see is like this one, completely functional building with a new layer, a new technological layer of PV modules in order to produce inside renewable energy, but with any interest from the point of view of the built environment, from the point of view of the architectural meaning of the spaces in where we live. So I would ask you, is this what we really want for our city and towns? Do photovoltaic systems have to be ugly by necessity? Should we really renounce beauty for the sake of sustainability? I would share with you today that there are more options, and probably we have to increase the use of these new options to train professionals in order to use new options. So have a look, for instance, at this fantastic skylight, this case from Onyx Solar, in which conventional glass is being replaced with PV amorphous, silicon amorphous glasses in order to have a very nice place, work, to live, to stay in general, with a very high quality in terms of daylighting, for instance, in terms of aesthetics in general. We have a closer look of the skylight. We can see very small junction boxes of the PV glasses, but you can see that the design of the elements is very clean. It has been done with a very with the main idea of reaching a very high level of integration of the system. You can see here another example, in this case from buildings of Google, in which the curved surfaces of the roofs of these buildings being covered with novel solutions. In this case, we have a new solution from SunStyle, in which the square PV elements are installed with 45-degree rotation in order to produce a totally different look of the surface in comparison with the traditional PV systems we saw in the photo of the typical solution. There's only a new word for the integration of PV coming from the digital printing of glasses. In this case, you can see, for instance, a PV facade from Chameleon Solar, in which the cells are hidden thanks to the digital printing of the glass. So we can produce images, we can produce different patterns using these new technologies. This is another example in which a typical cladding system for a facade has been replaced with a cladding system. If you have a close look, you can see the cells from a normal distance. The elements will appear like a traditional cladding element. So you know the new European Bauhaus project coming from the president of the European Union, Ursula von der Leyen, when she presented this new project, this new idea, said that we need to give our systemic change its own distinct aesthetic to match style with sustainability. This is why we will set up a new European Bauhaus, a co-creation space where architects, artists, students, engineers, designers work together to make that happen. So it's very interesting from my point of view. Consider that to match style with sustainability is just what BIPV do. So obviously we need to improve the use of distributed PV systems, but I think we cannot renounce of the beauty of our cities. BIPV, this technology, has this advantage in comparison with other energy production technologies. So what do we speak about when we speak about BIPV? I think that it's important to define these kinds of system. When we speak about BIPV, we are speaking about systems in which the elements replaces the conventional building components, like this fantastic mountain hut in the Alps. So the building envelope is not functional without the PV elements. And from the first 2 points, we can say that the BIPV elements should be multifunctional. We are not building a new, we are not speaking about of build the building first and then to add the layer. We are speaking about to design solar buildings. So it's very different from the typical system we are used to see in our cities, in which conventional PV modules are added to the building envelope, but the building envelope is only functional without the PV elements. The PV element generates electricity. It's a lot, but it's not enough. in my opinion. So cities are the core of the global climate change mitigation. And the question is, what can we do to make them more compatible with our planet? I would share with you the research project called RINGS BIPV, Innovation Innovative Global Solutions with Building Integrated Photovoltaics, which CMAT and UPM are collaborating in order to spread the use of BIPV. This research project is being founded by the National Spanish Program, research program oriented to the challenges of society. So we are working on two main projects in a coordinated project, advanced modeling and forecasting of the BIPV modules and system. Mainly, CMAT is working this topic. Jesus will speak about this research line. The BIPV solution for rehabilitation project at UPM mainly. So let me share with you the three main research lines we are working on in this project. The first one is the characterization under real conditions of BIPV elements. The second one is the self-sufficiency potential at urban scale. The third one is the BIPV for historical buildings. So I will speak briefly on the three main research lines. Regarding the first one, we have stored PV or BIPV showroom or demonstrator experimental pilot system in order to have data about the behavior of the different solutions we have in the market. So we are comparing, for instance, electricity production, obviously, but also superficial temperature or soiling or angular losses or degradation in order to have data we can use to train and to understand first the behavior of the elements and then to use them to architects to design building integrated PV systems. So we are collecting a lot of data, we are analyzing them, and I hope I will share with you in the next month some results from this analysis. So the second research line is about the assessment of the potential of the distributed PV generation to our cities. So in order to compute the self-sufficiency potential or how much we can cover the energy necessity of our city with distributed PV system, in the first step, we selected the different urban fabrics of the different neighborhood of, in this case, Madrid, but the methodology can be adapted to other places. Then we calculated the energy production and estimated the energy consumption of each building for an assessment of the self-sufficiency potential and show the results. We elaborated maps. So in this slide, you can see a little bit more detailed the diagram of the methodology. I cannot explain the details, but we use a lot of different tools in order to have data of consumption and generation. So, for instance, we use GIS information. We use LiDAR imageries, the PV, GIS, solar irradiance database, and so on. Also, we had to select different building fabrics, the clustering, the building typologies used in different zones of the city. You can see here a solar irradiation map. With this data, we can compute the self-sufficiency potential. You can see here as an example, depending on the urban fabric of the different neighborhood of the city, we can have as high as 90% of self-sufficiency potential, or as low as 10%. Obviously, it depends on the availability of surface to generate electricity on the electricity demand of each building. But it's very important from my point of view to some assessment, some number, some order of magnitude to have an idea of where we can reach the potential of covering the energy demand of city. Regarding the third research line, we are working about the use of BIPV for historical buildings. Why? Well, because there are a lot of historical or in general old buildings. In this case, we are mainly working about Europe, but also other cities. In Europe, for instance, about 1/3 of the buildings we normally use were built before 1945. So there are a great necessity of retrofitting of increase the energy efficiency of this building. To have an idea about the possibility of BIPV for historical building, we designed this methodology based on the analysis of case studies in order to have deep understanding of what can we do, what cannot do, and what are the main aspects to consider when we think about installing PV, a very technological solution in historical building. In a lot of cases are also heritage building or listed buildings, so we have to have a very high sensibility according to the importance of this building, the conservation of the buildings that we are speaking about. So I would like to share with you some examples of BIPV integration in historical buildings. The first one is a residential building in Italy. It's a villa in Bellano. And you can see that it's a very old building, built in the 19th century. Kilowatt installed on the roof. You can see that the PV is almost invisible because the design of the PV system was done considering the importance of not changing the aesthetics of the roof. So kilowatt is not a lot, but in this case, the PV power is really not the important thing. The important thing is showing that we can do retrofitting like this one without changing the aesthetics of the building. The example is from Australia. In this case, is a church, a cathedral. In this case, a new skylight was installed between the buildings with a glass very clear, a very clear PV glass. In this case, an amorphous silicon PV glass, but with a very high level of integration in the site where the skylight is installed. This is another example of a residential building, in this case in Switzerland, in which the full roof is covered with PV elements. The PV elements is the cladding, the waterproofing roof layer of the roof. This is another example in a multi-family residential building. In this case, in Switzerland also, with the full facade cover with the element with the cells hidden with this clear green color. Another example is this one in Madrid, in which an industrial building built in 1905 has been retrofitted, and the skylight has been made up, in this case, with V-glasses. So to conclude, we know that we need to improve the use of distributed systems in our cities. We need to spread the use of BIPV systems, and the system we design and we install are also beautiful, it's even better. So thank you very much for your attention. We will be happy to answer any question you may have in the Q&A session. Thank you very much.
Thank you very much, Lorenzo. And yeah, please feel free to ask questions in the box. You can find it up on the bottom, at the bottom with a question mark, questions and answers. We had already one comment. I included an answer. That is a bit subjective. I understand. This was my opinion that, well, it is possible to keep, yeah, the question was, BIPV sounds like a very good option. They can that can address both sustainability and architectural aesthetics. But do you think the 2030 race goals could be achieved without running into problems with resource depletion to build all the PVs that will be required to make this transition? And yes, I would say yes. I think there's this possibility to reach the targets without reaching the critical resource depletion barriers if things are well done. But to my understanding, BIPV will remain a small part of this market, at least in the near future. But
For sure.
maybe.
Yeah, I agree with you, Nuria. 2030 goal is very ambitious. BIPV is very small market today, but with a very big potential. This potential, I think, will not be exploited in the next 4 years a lot. So we are having an increasing use of BIPV system, but very slowly. There are other technology today that can be much more important in reaching this goal. For instance, the power plants that we have a lot, but it's important to know that we can include also the generation within cities, not only in the very big power plants. So I think that we have not the resource depletion problem about photovoltaics in general. I'm not an expert in this topic, but silicon is very distributed resource, and we need only few materials to manufacture PV cells. So I think that there are no problem of resource depletion.
Okay, thank you, Lorenzo. And there are other questions. The next one by Marin Tejada. How can these materials be sustainable if the area is prone to natural hazards and climate disasters such as Pacific Islands? And also, how about the fire safety aspects of PV panels? I don't know, Lorenzo, if you want to answer.
Sustainability of the solution, it depends on how the solution are built. So in general, we need only 1 year, or in some places only half year, 6 months, in order to cover the energy we need to produce the PV element. With BIPV, we have also the advantage that we are not using other building materials. We are not building new layer. We are using the same element for 2 objectives, for the energy, electricity generation, and for the architectural function. So in general, the sustainability is higher. About the fire safety aspect, this is a topic that has been applied a lot in the industry. Today, we can say that PV panels are very safe regarding the fire hazard, but we have to design and install the systems very well in order to avoid problems. For instance, we know in the typical self-consumption PV systems that most of the problems regarding fire problem and so on are not coming from the PV modules, are more related with the connectors. The connectors because because normally be mixed different things. No, we use MC4 connectors for all today, but sometimes we use connectors that are not built from the same company. So the cross connection be where the fire starts, or the ignition point of the fire accident, but not the module, the PV module itself. It's the use of the different connectors that can be problematic.
Yeah.
That's
something to add to the fire safety. It is a very difficult issue because there is not really an harmonization between the countries. But there is a very interesting recent work from different countries collaborating in, for example, Task 15 in the IEA PV power system Task 15, that it is a task devoted to BIPV, and there are some reports addressing this, but it is something very difficult to harmonize, but a key issue for sure for the BIPV systems. Also, there is a question from Shoina. Thank you for the presentation. My queries are, what is the storage system for this transition? Is it economically and structurally feasible? No, sorry, there's another one before. Sorry, I jumped before. First, thank you for the meeting. I have a question about the new technology PV systems such as half-cut, bifacial, and top-con PV panels. Is there any specific simulation tool to calculate their energy generation if we use them as BIPV systems? Well, the answer, I can maybe give the answer, or you can.
Yeah. In general, there isn't a specific BIPV tools, simulation tools. We normally have to simulate the behavior of the PV system with a specific PV simulation tool. There are a lot in the market, and they takes into account the different technology of the PV cells and half-cut, bifacial, etc. But to analyze the thermal, for instance, behavior of the BIPV system in terms of thermal protection of the buildings, normally we have to use different tools that are more from the architectural construction sector. So it's a very it's a very complex task to have an overall idea of the effect of the BIPV on the building, including aspects, lighting aspects for daylighting, for instance, in light or windows or curtain wall, for instance. We have to simulate with different tools, and we have to have the balance without a specific tool. Be it overall, we have to do it by part, the different aspects, and then have the balance inside the tools themselves. So, but from the PV point of view, specific tools, there are a lot of them in the market, are able to take into account the specific characteristics of the PV cells. So, regarding the storage system, we say that it depends the viability, the economical and energetical viability of the storage system depends on the curve of the consumption of the building. If we have a lot of the consumption in the night, be able to install a storage system. If we have a lot of consumption in the day, hours? Probably not. It also depends on the importance we consider the importance of the possibility of have energy if the grid electricity have a problem, or if we have a blackout things or problem very frequent in some places, and not so frequent in another place. So I think that to establish if we have it's a good idea to include a storage system, we have to analyze each project. We cannot say a general rule.
Okay, and there is another question. What about the maintenance of such PV systems when integrated in an existing building? Usually PV panels are affected by performance reduction over time, so don't you think that the need to replace these integrated systems every few years could be a significant limitation in terms of impact on the building occupants due to the too repeated invasive maintenance work?
Well, really, the warranty of the typical PV modules are very about 30 years. I can see the product warranty and the production warranty, 25 years normally. And in the BIPV sector, the value are very close. Sometimes they are also a little bit higher. So have probably we have to replace the BIPV elements during the lifetime of the building, but maybe each 30 years. So it's not very, it's not a lot, I think, in terms of impact on the building use. Sometimes we can also do the replacement without interrupting the use of the building. So I think it's not the very a critical issue in order to establish if we do the BIPV facade or not. It's not the point, I think.
No. And regarding, for example, cleaning the facades or whatever, is not more than cleaning a normal facade. And it is true that solutions for accessing the BIPV modules should be included in the maintenance, but the maintenance and operation book should include all these solutions, all these possible replacement. But as Lorenzo said, it is true that the warranty of the PV modules usually is larger than the warranty of some other elements of the envelope. So this shouldn't be really an issue. Okay, I think there are not more questions for this first part of the webinar. So we change to Jesus Polo. Sorry, Jesus. And I give you the floor for the second presentation.
Okay,
Yes.
thank you very much, Nuria. I'm sharing my screen. So this presentation deals about modeling and simulations of BIPV systems. And the main objective is to give an overview and a review of a modeling simulation, remarking the specific features and singularities that we find in BIPV system comparing with conventional PVs. This overview is presented through several samples of works, particular works we have done within the RINGS project in CIEMAT with the collaboration of UPM. So to start, it's interesting to see how we model the PV performance. So what are the different steps in modeling a PV system performance? So if we see at the information in the PV performance modeling collaborative group, which is a very active group in modeling PV system. This is the group that maintains the PV toolbox. There are a lot of words. They identify the steps in modeling PV performance in different groups. We have a first group regarding the weather data. We have to compile information of solar irradiance, temperature, meteorological conditions, and this information is used in how has to be processed to calculate the incident irradiance in the PV panel, the shading condition, and so on. A second group is focused on the electrical and technical characteristics of the modules to be used. Then we have another group referring to the array setup. In other words, how many strings do we have, the configuration in parallel or series configurations, and so on. The fourth group is for the inverters, for the DC to AC conversion, the technical characteristics of the inverter. And finally, what we are going to calculate or determine is to find the AC system output, and we have to consider different losses and metrics that happens in the whole process. So this is the general overview of how normally we model a PV performance and what happens in BIPV. So I would like to share this slide because it's like an evolution from what we know as building attached PV, which is the use of more similar to conventional PV, but place conventional PV systems in a building. And we have seen an evolution from this situation to a completely integration of photovoltaics in the buildings envelope. And this situation reflects this observation. We have a shading between three main objectives. The energy objective, we want to generate energy. We want to generate energy and use these generators as an element, a constructive element. So these generators must be inside, completely integrated in the envelope of the building. And as Lorenzo has presented with many examples and has remarked, also we want that the aesthetic design takes importance. So this goal is these three features are, in my opinion, balanced in the role they face in BIPV. So with this situation, we can infer that when we have to model BIPV, we are facing some challenges. Why? Because obviously BIPV is characterized by very different system configurations and very particular boundary conditions compared to conventional PV. We have many different ways of installing generators. So we have tiles, canopies, windows, rooftop, balconies, facades, many different elements with very different boundary conditions. So this is a challenge, and this is what makes somehow different the modeling, the strategy for modeling a normal PV conditions, BIPV conditions compared with the conventional one. And tools. So we have, indeed, we have many tools for depending on the different approaches. And I would like to remark, for instance, this table. This table was taken from a very interesting paper in Energy and Buildings journal. Is the reference. There is a list of different tools with remarking the different characteristics or approaches this tool do for different things. For instance, for weather data, if we are able to work with TNY, or we are taking data from satellite-derived solar irradiance services. Regarding the configuration of PV modules and inverter, the layout, the way we simulate solar radiation with the transposition model, how the shading is taken into account. If we use, for instance, sky view factor or ray tracing methodologies for computing the incident solar irradiance, the way of losses, how losses are treated, and also and the timestamp of the results, if we are interested in energy yield, in monthly or more detailed hourly power or other variables. So let's say one first step that belongs to modeling BIPV or PV inside a urban environment refers to what we know as PV potential in urban environments. I would like to review a little bit this part of the modeling works, because the first step in every decision to make on a district or a city or whatever, or a urban region, is to detect or determine which parts, which areas are more available or more feasible to be used as PV generators. So we have to distinguish between what is the physical potential, that is basically to estimate the solar irradiance at pixel level in a spatial domain, in a region, in a city, in a district, in a neighborhood, or whatever. The next step is the geographical potential, where we have to take into account the topology of the spatial domain. In the physical potential, we treat the domain like a flat terrain, and we are only compute the solar irradiance or solar insolation. And in the geographical potential, we need the 3D topology to estimate the sky view factor, the shading effects by the obstacles surrounding each building. And the result in geographical potential is the solar radiation incident in each element, take it into account the surrounding. And the third part, the third step, is the technical PV potential, which basically is to convert this incoming incident irradiance for each element into solar photovoltaic potential. So we need to put the efficiency model into the equation and to convert incident solar irradiance to PV power. So I would like to go further in this part of the modeling and to explain a little bit the methodologies for solar cadastres. Normally, what we need, as I mentioned before, we need to incorporate in the modeling information of the 3D scene. That is the heights of every building, trees, everything what is in the domain. And this is done by the digital surface model. The digital surface model is more than a digital elevation model. It's not only the elevation of the terrain above the sea level, but also we have to include buildings, all the elements that are installed in the ground. How do we do this digital surface model? One very feasible methodology is by using LiDAR information. LiDAR information can be transformed with very available tools with geographic information system or libraries like LAS tools in the digital surface model, DSM. This is an example of a digital surface model for the CMAT campus, for part of the CMAT campus. You can see this, and with a 3D view, you can see this digital surface model in 3D view. I would like to remark the round edges, because you can see that the buildings are not perfectly delimited, perfectly square. They are somehow rounded. The edges are not perfect. And this has to be is related to the uncertainty of the digital surface model. So with this information, we can make what we call solar cadastres. This is an example of this is the CMAT campus, or this is a neighborhood in Madrid. The solar cadastre is a pixel level information, as you can see here. And as Lorenzo mentioned before, we can process this pixel information and derive more advanced information, like the self-sufficiency index, which is working at a cadastral level with the buildings itself, with the building footprints, with information of the consumption of the building, with the number of floors, a number of families living, and so on, with some features of the rooftops and the orientation of the rooftops. And finally, the combination of this information with the solar cadastre using geographic information systems can offer more processed data like self-sufficiency or self-consumption index or whatever. So like I mentioned before, the DSM, the digital surface model, is an important part in the solar cadastre, but we have to, we don't forget that the digital surface model is uncertain. So then here is an example of two different methodologies. We have created a digital surface model with LiDAR data, or with photogrammetry, or we can use Google Earth features. And these differences at the end will create some kind of uncertainty in the estimation of the PV potential in a solar cadastre. So we need to use a digital surface model that are as accurate as possible, and that means to fit in the building edge with the footprint of the buildings. We can combine LiDAR information with other cadastral information like OpenStreetMap or other systems to create a more reliable and more accurate building footprint. It is recommended also to use DSM separately for buildings and for vegetation, to treat separately, because vegetation has some capacity of transmissivity, of transmission of light, and this is different than buildings which are completely opaque for the light. And this is an example, this below is an example of how combining LiDAR information with OpenStreetMap to create a better, more accurate envelopes of the building's footprints. This is again the TMAT campus. And there are other possibilities. For instance, CityGML with 3D blocks. This is getting right now almost a standard to create 3D scenes of cities or neighborhoods. So, okay, when we have a digital surface model, we can estimate with more accurately the incident irradiance, which is one part of what we need in modeling a BIPV system. This is an example of a building in TMAT with a rise in the east, south, and west facade, where we use the digital surface model and satellite-derived information to compute the solar irradiance at each facade. And this slide summarizes quite well the methodology. We have one part is compiling information of the solar irradiance at ground level that can be done by satellite-derived tools. For instance, PVGs is a well-known tools, or CAN, the Copernicus Solar Radiation Services, is another tool that delivers hourly or sub-hourly data of the main components of the solar irradiance. We have to create a digital surface model, and these two inputs are used in a transposition model, for instance, per transposition model, to convert the solar irradiance components that we receive from satellite tools to the solar irradiance incident in the surface, and in our case, in the facade. So what we call the POA irradiance, the plane of array irradiance. We have to modify the best transposition model to incorporate the SkyB factor, because it's a facade or a building. The SkyB factor is different, because we have to take into account the topology surrounding the receiving surface. It's not like a conventional PV. Exactly. We have to take into account the shading also. And finally, here is an example of, in our building, the SkyView factor of the different facades. Here is an example of computing the shading every hour. And this is the east facade with has 10 meters above, has a string of large trees. We can see here how at different times in the day the shadowing is evolving. And finally, we can compute the annual irradiation in the facade. This is one example here in TMAT. So this is the part of the solar irradiance panel. Next step is to compute the PV performance of the BAPV system. Most of the examples I'm giving here are focused on facade, because they are real examples we are working with in TMAT and UPM within the RINS project. So what about if we using conventional tools? For instance, some system advisor model and PVCs are, I would say, that are standards. We already use one of them or very similar tools to model PV performance. And we can use it to model the PV performance for a BIPV system in a facade. It's just two examples of comparing sun and PVCs with experimental data of monitoring. Here in our building, we have this is south facade, and this is west facade. You can see that we are able to reproduce quite well the seasonal behavior of the power performance. These are modeling are done with using 1 year of satellite derived information as meteorological input, in particular from Copernicus, from CAM's information solar radiation service. And the performance is quite well in this case because the shadowing is not a big issue in these two facades. But however, in the east facade of our building, the presence of these large trees is a challenging. And we can see here, if we compare the situation using some without modeling, without imposing any particular shading system in this facade, with creating a shading with the 3D shading tool that are available both in SAM and in PVCs. We can see how some situations where the shading is very important, how sensitive are the modeling to the shading condition. And when we are imposing as 3D shading, the modeling results are much better, and the goodness is better, and the fitting, the accuracy is much better. But these tools that are available in some PVCs are not the best, probably not the best tools to compute the shading, because you can see here that even we are imposing some 3D shading, we have also important uncertainties. So this is another example where we incorporate the DSM, the digital surface model, in PVCs, and how are we able to improve our results. Here is the east facade. You can see here the PVCs with the 3D shading tool that has, and when we read the topology with the DSM, we have much better results to the experimental one. So there is still work to do, and we have to develop methodologies to incorporate a real, the closely or the more accurate real 3D topology we input in the model, the better, and the better the accuracy of the model, particularly when we are facing important shading features. So before ending, I would say that I would like to tell you a few words about the spectral mismatch, because we have to face the shading. This is a very particular situation that BIPV has to handle with, but there are obviously spectral mismatches can be also a part in the modeling, because you can see here one day of the solar spectral at different north, east, west, or south facade, comparing with the standard. And we can see that how the spectrum changed completely compared with the standard, which is where normal spectral mismatch are rating in PV modules and in BIPV modules as well. So these changes suggest that we have to use a particular spectral characterization in the case of BIPV because the incident spectrum differs a lot compared to a conventional PV. Because the tilt angle now 90 degrees is large, and the orientation plays an important role. This is a model we have proposed for computing the spectral mismatch from the solar geometry, the angle of incidence in the facade, and also the optical depth and the precipitable water. And here we can compare this model in the particular situation with very well-known models like the Kim model for First Solar or Caballero model. So in the case of BAPV, sometimes we have to account in a different way the spectral mismatch. Okay. And this is what I wanted to share with you. Just to mention that the RINS BIPV project, here is the web page. We are, as Lorenzo mentioned before, we are working in different aspects of trying to contribute to bring new solutions that help the BIPV to be incorporated in the cities, and particularly in the retrofitting actions. So I'm here glad to answer any questions you might have. Thank you very much for your attention.
Thank you very much, Jesus. There is one question to you I can read it. Hi, Dr. Jesus Polo. In the comparison between the PV modeling with PVsyst and the experimental results, did you use the same weather data, real data?
No, we use the same weather data, but we use satellite-derived irradiance. The meteorological input to the models, to the both models, was the same as and was not the experimental data we have in solar irradiance. We use satellite data for 2019 in this particular case. This is interesting to make this kind of comparisons, because in any analysis or study that the people or engineers or any stakeholders have to done with a specific building, normally they do not have measurements on their building, solar irradiance, and they have to use available information of meteorological input to use the proper model and to compute the energy yield and the performance of the in this case of this BIPV in facade system.
Okay, thank you. Any further questions? We have some time to answer more questions.
There is the comparison. Yeah. This is the question. Yeah, okay.
Yeah, okay. Okay, if there are not further questions, then I give you the floor, Laura. Please.
Yes, so I would like to thank you all for your questions and for engaging so actively in the discussion. And a special thanks again to our webinar chair, Dr. Nuria Martin-Civile, and to our speakers, Professor Lorenzo Olivieri and Dr. Jesus Polo, for your valuable insights and clear answers. As a reminder, the webinar recording will be available on our website next week, and your certificate of attendance will be accessible shortly through your SciForum account. We appreciate your participation, and we hope to see you at our future events. I wish you a great day or evening wherever you are in this world, and thank you all again.
Okay, I had some, I took some notes during the presentations. I'm going, can I go through them?
Sure, please.
To conclude. And maybe there's another question in the meantime. What if we want to work for future weather and irradiance project? This goes to Jesus, please.
Yes, this is a very interesting question because the next step in modeling is to forecasting what are we're going to find in the future, days ahead or months ahead, or even if we are more ambitious, we have to use climate change scenarios to compute the energy yield we expect in actuation of in a building or in a neighborhood in the next 30 years or 40 years or even more than that. I have not seen yet works on this for BIPV specifically for in this situation, but I think that it is interesting because in other activities regarding PV or solar system or renewable system, there are scenarios for climate change, scenarios for future. We have some models that predict the meteorological conditions for the next 100 years or whatever. And I think that this is a next step that is going to be included in the modeling activities somehow to analyze how the different climate change scenarios, optimistic, pessimistic, whatever, have been impact in bringing this BIPV system in a city. How is expected to reduce the CO2 emissions, the energy consumption according to different scenarios, what means different possible mitigations or actuations that we can do in the future.
Okay, perfect. Thank you, Jesus. Then, well, some conclusions to close this webinar. I don't know what is happening. Yeah. So first, to remind that the current framework is in most countries and regions in the world is favorable for PV in buildings, for example, the European Directives, etc. But PV in buildings can be BAPV or BIPV. BAPV, building attached photovoltaics, BIPV, building integrated photovoltaics. And despite the advantages of BIPV in aesthetics, sustainability, material saving, safety, etc., it is still underrated. And why? We wonder why. Well, there are several studies and well, in particular, Task 15 has go deep into these reasons, the barriers for BIPV. But also important to say that the role of cities in the climate change mitigation is very important, and BIPV is an optimal solution, especially in retrofit actions. In Europe, we have heard in the first presentation that more than half of the buildings were built before 1969. So action has to be taken in retrofit, energy retrofit, and in this case, BIPV can be very useful. It is compatible with heritage buildings. Good examples, we have seen very good examples and a methodology to perform this kind of projects. Also, important approaches to determine the PV self-sufficiency potential in PV in buildings. And next step will be in BIPV, also including facades. BIPV simulation, BIPV potential can be reached if first we consider the PV modeling and simulation tools from weather data to system losses determination. This is a task to do in regular plants. But what about BIPV performance modeling? The different boundary conditions of BIPV modules compared to PV modules in regular plants. For example, higher operating temperatures because of less ventilation, more frequent partial shading, non-optimal position of the PV modules, which increases angular losses, spectral losses, etc., different colors, sizes, etc. These are some features that have to be taken into account in the simulation. So are the PV simulation tools and building tools sufficient? This is one question. Jesus has already given some answers to this. The first step for BIPV simulation, of course, is always the solar radiation determination. And in this sense, the solar radiation maps for the building envelopes are very useful, the solar cadastres, and so on. So there's a lot of work undergoing here and very interesting perspectives for the future. We already have seen that the digital surface model can improve the modeling results of the available tools. So this is a first step. And well, as a general conclusion, I would say BIPV can play a relevant role in the design of future cities, although there are still several barriers to overcome. And there is margin also for research, development, and innovation. So I encourage you to invest in BIPV because it means investing in a sustainable and resilient future for the cities. And then thank you very much for your attention. Thank you very much also to MDPI. And I hope this webinar has resulted useful for you. So thank you very much.
Thank you very much, Dr. Tivele, for the conclusions and the closing remarks. And thank you again for the speakers for accepting our invitation. And we hope to see you at our future events as well. Thank you very much.
Thank you.
Thank you very much, Laura.
Thank you very much. Thank you, Laura.
Thank you.